Welcome to Dr. Boxy Teaches Electromagnetism. In the previous two lessons, we discussed differential calculus. We introduced the notion of fields and we looked at different kinds of derivative of these fields, specifically the gradient, the divergence and the curl. In this lesson and the next couple of lessons, we will look at integral calculus. We will introduce different kinds of integrals we will need, line integrals, surface integrals and volume integrals, and we will talk about integral theorems that will allow us to interpret the three special kinds of derivatives we introduced previously. So let us get started. The Riemann integral for functions of one single variable is introduced in the following context. We start with some function f of x, so let's say this here is the function f of x. And we choose some points on the x-axis. Let's say this here is A, and this here is B. The objective is to determine the area enclosed horizontally between A and B, and vertically between the x-axis and the function. So we are looking for this area here. Now, to do that, we will subdivide the interval AB into smaller intervals and approximate the area we're looking for in each of those separately. So let's call A x0, and then we choose some point, let's say here x1, x2, x3, etc. until we get to B, which is xn. So we now have we partitioned the interval A to B into n subintervals. And in each of those subintervals, we choose some point. Let's say in the first one, we choose this point and we call it C1. In the second one, I choose this point and I call it C2. In the third one, I choose this one and I call it C3, etc. Now, within each of those subintervals, we will approximate the area we're looking for by the area of a rectangle, where the width of the rectangle is the actual width of that subinterval, and the height of the rectangle will be the value of the function at the point C we chose. So for instance, in the very first interval, the value of the function at the point C is this value here, and so this will be the rectangle we consider, and so the area we are looking for in the interval x0 to x1 will be approximated by the area of this red rectangle here. For the second interval, this is the value, and so we will look at this rectangle. The top should be horizontal. Then in the third interval, we are looking at this rectangle, etc. And so we have n different rectangles, and we will look at the area of each one of them. So let us look at the ith rectangle. Where I runs from 1 to n. So if we look at that ith rectangle, it looks something like this, where its height is f at the point ci, and its width has a value of delta xi, where we define delta xi by xi minus 1, so the width of that subinterval. And so the area of that rectangle is the product of its height and its width. So the area of the ith rectangle is equal to f of ci times delta xi. So this is the approximation of the area we're looking for. for the ith rectangle, and then we add them up to get the area under the whole interval between a and b. And so the area we are looking for is approximately equal to the sum for I going from 1 to n of f of ci delta xi. And this sum is known as the Riemann sum. Now we can make the approximation better by taking more and more of these subintervals, so making all of them narrower, and as n increases, we hope that the approximation becomes better and better. Now there are some conditions for this to hold. It's not necessarily true that it becomes better for any function, but under certain conditions, taking the limit in a specific way, we define the Riemann integral from a to b of f of x dx. The definition for this is the limit of n going to infinity of those Riemann sums. So of I equals 1 to n f of ci delta xi. Now this definition works under the assumption that that limit exists, first of all, that limit exists and doesn't depend on the choice of our xi, so how we subdivide that interval, that it doesn't depend on which points we chose within each subinterval, so which ci's we chose. And those conditions are not necessarily true for any function. And so there is some mathematical theory behind this to make sure that we are considering cases, that we are considering functions where this actually works. Now, all of these nuances will be left for a course on real analysis and calculus, which will come in the future. But in the context of this course, in the context of a physics course, I will not focus on the mathematical nuances. We will assume that all these things work out so that that limit exists, that it is well defined, and we will use this, and any function we will encounter in physics will have these properties. So there is little point in the context of a physics course to go into the pathological cases that mathematicians find very interesting and that are important in mathematics, but I will leave those for a future course in mathematics. So this is the definition of the Riemann integral for functions of one single variable. We now want to generalize this to something known as a line integral. We specifically want to introduce the line integral for vector fields, for vector functions. And so we start by considering some vector field, v of x, y, and z. And remember that the way to interpret this is to say that there is a vector at every single point in space. And now we consider some three-dimensional lines, some path in 3 dimensions. Let's say this line here. This is some 3-dimensional curve. It starts at a point that we call A, and it ends at a point we call B. And just like we did with the interval AB for the Riemann integral, we will subdivide the curve into smaller parts. So remember I called it x0, x1, x2, but because it's not on the x-axis this time, I will just give it a more general name. We call it L0, L1, L2. So the point A, I call that L0, and I choose some point L1 on the curve, further down L2, still further down L3, etc., until we get to B, which will be Ln. So in this way, we divided the curve now into n parts. And just like we did with the Riemann integral, within each of those subintervals, we chose a point. So we choose in each of those subintervals a point. Let's say in the very first one, I choose this point and I call it C1. In the second one, I choose this point. I call it C2. In the third one, I choose this one. I call it C3, etc. Now we want to focus on one of those subparts of one of those small pieces of curve. So let's look at the ith one. I again runs from 1 to n. And if we look at the ith part, it looks something like this, where this point is Li minus 1, this point is Li, and within that part of the curve we chose some point, let's say this one here, which we called Ci. Now we are dealing with a vector field, and that means that at the point Ci there is some vector. So let's say that it is this vector here, which is v of Ci. Now if we think back of what we did with the Riemann integral, we evaluated the function f at the point Ci we chose, and we did that for each of those subintervals, and then we added them together. Well, we want to do something similar here. In each of those parts, we want to evaluate the function at the point we chose, multiply it by the length of the interval, which is what we did in the previous case also, and then add all of these together. But we don't simply want to add the vectors, we only want to look at that part of the vector that points in the direction of the curve we are following. What do we mean by that? Well, to understand it intuitively a bit better, let's first look at something we know from mechanics, which is the work done. Imagine we have a mass, a box of mass m, and some force is applied on it, force F, and that force has an angle theta with respect to a horizontal line. And as a consequence of this force, the box moves horizontally a distance delta x to the right. So the vector delta x represents the displacement. What is the work done by that force during that motion? Well, the answer is it's not simply the force times the displacement. It is only the component of the force in the direction of the displacement that does work. The component of the force perpendicular to the displacement does no work at all. So if we want to calculate the work, we only need to look not at F itself, but at its component in the direction of the displacement, which is F cosine theta. We need to multiply that with delta x. And notice that this expression can be written as the dot product of F with the displacement vector delta x. So what we want to do is something similar for the line integral. So again, we look at the ith part of the curve, Li minus 1, Li. This here is the point Ci. And at that point, there is a vector v of Ci. And the displacement will be represented by a vector going from Li minus 1 to Li, this green vector here, which is delta Li. And now we do something similar to what we did with the work. We will take the dot product of the vector with the displacement. So in the case of the work, the vector was the force, the displacement was delta x, so we dotted F with delta x. In this case, we will take the dot product of V of Ci with delta Li. And this is the value that we want to add for each of those subintervals. So this is the number we get, the value we get for the ith interval. And now we want to add these for all of those subintervals. And so we get the following expression. It's the sum for I going from 1 to n of V Ci dotted with delta Li. So this is a Riemann sum kind of expression, and we do a similar limiting process in such a way that n goes to infinity, in such a way that the size of each of those sub-intervals becomes smaller and smaller. And as we take that limit, we get something which is known as the line integral. So as n goes to infinity, we get something which will be written as v dot dl. And we put a p under the integral, and it represents the path, the trajectory we followed from the starting point to the end point. So this is the definition of the line integral. And once again, just like with the Riemann integral, there are nuances that need to be taken into account. We need to make sure that this limit exists, that it doesn't depend on the CIs, and it will turn out in a mathematics course on this that it works for many vector fields, but not all of them. It turns out that it works for many curves, for many lines, but not for all of them. And again, in the context of this physics course, we will assume all of these conditions are met and we will just work with it. And I refer you to a future course in mathematics in which we will actually discuss the nuances of all of this. Now, there are a couple of remarks to make on this line integral. The first remark is that the path can be followed from A to B or from B to A, and we get the same value up to a minus sign. So if we take this path, for instance, this is the point A and this is the point B, and if we consider the path going from A to B as the path P1 and the one going from B to A as the path P2, then the integral, the line integral of P2 of V dot dl, so going from B to A, is equal to minus the integral of P1 of V dot dl. So following the curve in the opposite direction gives us the same value up to a minus sign. A second remark is that this line integral is really a generalization of the Riemann integral we looked at for functions of one single variable. And why is it a generalization? Well, if we just take the line we consider for the line integral to be the x-axis, so we take a line along the x-axis, what we get is exactly what we have for the Riemann integral of functions of one single variable. And thirdly, if we consider a closed path, so for instance, think of the following path. Here is the point A, and we follow some curve, and it closes up on itself such that the point B is equal to the point A. Well, in that case, the line integral, which is then known as a closed line integral, will be written in a similar way, P V dot dl, but we will put a circle on the integral to emphasize the fact that it is a closed line. It will not affect the way it is calculated. We will see that in a second, but we will encounter many of these in the context of physics, and so it's important to know the notation. If we see a line integral with a circle on it, all it means is that we are considering a curve, a line that is closed. So let us see how to calculate such a line integral. As an example, we consider the following vector field. It is a vector field whose x component is equal to y squared, its y component is 2x times y plus 1, and its z component is 0. And we will look at two different paths going from A to B, where A is the point 1, 1, 0 and B is the point 2, 2, 0. And the two paths we will consider are these two. The red one, path number 1, going from A first to the right horizontally and then vertically upward to B, and path 2, which will be a diagonal line, the green one, going directly from A to B. For these two paths, we want to calculate the line integral. And once we did that, we also want to calculate the closed line integral of V, going from A to B along the red line and then going back from B to A along the green line. So let us start with the very first line, so with the red line, and we will divide it into two parts. The horizontal part, which I call part 1 of path 1, and the vertical one, which will be part 2 of path 1. So let us look first at 1, 1. We need to calculate the integral of v dot dl. Now remember that dl is the general expression for a displacement, and it has the following form: dx times x hat plus dy times y hat plus dz times z hat. Now, along this very first part, there is no motion in the y nor in the z direction. It's only x that changes. And so dy and dz, both of them vanish. So dl is simply dx times x hat. Notice also in the figure that along this very first part, the x goes from a value of 1 to a value of 2, while the y remains at a constant value of 1. So if we want to calculate now v dot dl, remember that one of the ways to calculate a dot product is to multiply their x components together plus multiplying the y component plus multiplying the z components. But the y and the z component of dl are both 0, so we're left with the multiplication of the x component of v, which is y squared, with the x component of dl, which is dx. And in this very first part, the value of y is a constant value of 1, so we can just plug in 1 for y and we get 1 squared dx, which is simply dx. And so the line integral along this very first part of the curve of v dot dl is equal to the integral of v dot dl is dx, where x ranges from 1 to 2. And the integral of dx is simply x, which needs to be evaluated at the boundary, so at 1 and at 2, and we find 2 minus 1, which is equal to 1. So the integral along the first part of path number 1 is 1. We now look at the second part. In the second part, x remains at a constant value of 2, while y goes from 1 to 2. So this is path 1, part 2. In this case, the vector dl, there is no motion in the x direction nor in the z direction, so we're left with dy times y hat. And if we calculate the dot product of v and dl, we get the multiplication of their x components, which is 0, plus the multiplication in the y direction, in the y components, which is 2x times y plus 1, which is this is the y component of v, multiplied with the y component of dl, which is dy, plus the multiplication of the z components, which are 0. And in this case, we can replace x as a constant value of 2, so we can just plug in 2 for x, and we find that v dot dl is equal to 4 times y plus 1 dy. And so the line integral over the second part here of v dot dl is the integral of 4 y plus 1 dy, where y ranges from 1 to 2. Now the 4 at the front can just come out of the integral, and the integral of y plus 1 is y squared divided by 2 plus y, And all of this needs to be evaluated at 1 and at 2. And we find the 4 remains at the front. And now if we evaluate everything at 2, we get 2 squared divided by 2, which is 2, plus 2, minus evaluating the same quantity at 1 gives us 1/2 plus 1. So we find that this is equal to 4 times 2 plus 2 is 4, minus 1/2 plus 1 is 3/2. And if we multiply out the bracket, we found 16 minus 4 times 3/2 is 6. And so we find that the answer is 10. And now to sum up, what we want to do is to calculate the full line integral along path 1. And that line integral along path 1 is the sum of the integral along part 1 of path 1 plus the integral along part 2 of path 1. Now the integral along the first part, as we saw before, was 1, and the one along the second part was 10, so we find 11 as the answer for the line integral along path 1. Now we want to look at path 2. And for path 2, we have that the value of x and y remain equal throughout the motion from A to B. We move along that green diagonal where x and y are equal to each other. And that also means that dx and dy equal to each other are equal to each other along the whole path. So because of that, dl is equal to dx times x hat. Plus we should have dy times y hat, but dy is equal to dx, so it's dx times y hat. Plus there is no dz term because there is no motion in the z direction. And so v dot dl is in this case equal to the x component of v, which is y squared, multiplied with the x component of dl, which is dx, plus the y component of v, which is 2x times y plus 1, multiplied with the y component of dl, which is dx again, plus the z components, but both of these are 0. So we get this expression for v dot dl, and because we have that x and y are equal along this trajectory, we can replace all the y's in this expression by x's. And so we find x squared dx plus 2x times x plus 1 dx, and if we collect all the terms, we get 3x squared plus 2x dx, and we want to integrate this along path 2. So we just found that v dot dl was 3x squared plus 2x dx, and so the integral along path 2 of v dot dl is equal to the integral of 3x squared plus 2x dx, where x ranges from 1 to 2. And so we find the integral of 3x squared is x cubed, plus the integral of 2x is x squared, and this needs to be evaluated at 1 and at 2. And we find, evaluated at 2, it's 8 plus 4. Evaluated at 1, it's 1 plus 1. So we get 12 minus 2, which is 10. So this is the result of the line integral along path 2. And finally, the last thing we wanted to do is to calculate the closed line integral of v dot dl, where we go from A to B along path 1, and then we go back from B to A along path 2, or rather along the opposite of path 2. So that means, remember, if we follow the opposite direction, we get an extra minus sign. So that means that we need to calculate the line integral along path 1 of V dot dl minus the line integral along path 2 of V dot dl. And we calculated already these two. The first one gave us 11, minus the second one gave us 10. And so we find that the closed line integral for this function along this specific closed curve gives us a value of 1. So this is how to calculate the line integral of some vector field. In the next lesson, we will look at surface integrals, volume integrals, and how to work with them. I'll see you then.